the constant of integration, and the family of antiderivatives. Good morning. So, building on what we've already covered in the previous section, we firmly established that integration and differentiation are essentially opposite operations. One undoes the other. Think of them as inverse functions, much like squaring a number and then taking its square root. Now, this leads us to a really important question. If someone hands you a derivative, meaning they tell you the rate of change of a function, can you uniquely determine what the original function was? It seems straightforward, right? But it's trickier than it appears. We'll see that there isn't always just one original function. There's a bit of ambiguity, and to understand why that ambiguity exists and how we deal with it, we need to introduce a crucial concept, the constant of integration. We'll be diving into what that is and why it's so important in the following slides. This constant is the key to unlocking the full picture of antiderivatives, and we'll explore how it creates a whole family of possible solutions. So keep this question in mind as we move forward. Can we find the exact original function, or just a family of them? Okay, let's begin with slide 1. The effect of constants on differentiation. First, let's recall a really fundamental rule of differentiation. It's something you've definitely seen before. The derivative of any real constant is always 0. What do I mean by a constant? A constant is just a number like 2, -5, or pi. So if we have a constant, let's call it c, then the derivative with respect to x of c, and I'll say that as d over dx of c is equal to 0. It's a very simple but crucial rule. Now let's see how this plays out with a slightly more complex function. Consider the function f of x, and I'll say that as f of x, which is equal to x squared plus 5. Notice the plus 5 part, that's our constant. To find its derivative, we can use the sum rule of differentiation. The sum rule simply states that the derivative of a sum is the sum of the derivatives. So the derivative with respect to x of x squared plus 5 is equal to the derivative with respect to x of x squared, plus the derivative with respect to x of 5. Now, the derivative of x squared is 2x, and remembering our earlier rule, the derivative of the constant 5 is 0. Therefore, the derivative of f of x, which is x squared plus 5, is 2x plus 0, which simplifies to just 2x. Let's look at another function to reinforce this idea. Consider g of x, which is equal to x squared minus 10. Again, we have x squared, but this time we're adding a different constant. Let's differentiate g of x using the same sum rule as before. The derivative with respect to x of x squared minus 10 is equal to the derivative with respect to x of x squared, plus the derivative with respect to x of. The derivative of x squared is still 2x, and the derivative of is, of course, 0. So, the derivative of g of x, which is x squared minus 10, is also 2x plus 0, which simplifies to 2x. Now here's the key observation, and it's really important. Both f of x, which was x squared plus 5, and g of x, which was x squared minus 10, are different functions. They're not the same, but when we differentiate them, we get the exact same derivative, 2x. This demonstrates that multiple different functions can have the same derivative. This is why, when we're trying to find the original function from its derivative, which is what integration does, we can't pinpoint just one original function. We'll see on the next slide how we account for this ambiguity with something called the constant of integration. Okay, so let's move on to slide 2. As we discussed on the previous slide, we're starting to explore why finding the original function from its derivative isn't always straightforward. This slide will help us understand why that is. The concept of the constant of integration. Okay, let's move on to slide 3. Now, remember from the previous slides we discussed how differentiation essentially undoes integration. But as we saw with the examples of functions like x squared plus 5 and x squared minus 10, different functions can actually result in the same derivative. Both of those functions differentiated gave us 2x, so this leads us to a crucial point. Since multiple functions can share the same derivative, it means when we're trying to reverse differentiation, that is, finding the antiderivative, we can't pinpoint a single original function. There isn't just one answer. Because of this, we have to acknowledge that there might have been a constant term in the original function before we differentiated it. Think back to how the derivative of any constant is always 0. That constant term would have vanished when we took the derivative. To represent this unknown constant, we use the symbol c. This c is called the constant of integration, or sometimes just the arbitrary constant. It's a placeholder for any real number. Therefore, when we find the antiderivative of a function, we always add plus c to the end. This plus c isn't just a formality. It's essential because it accounts for all possible constants that might have been present in the original function before differentiation. It ensures we're representing the entire family of possible antiderivatives, not just one specific instance. In the next slide, we'll really solidify this idea of a family of antiderivatives. But for now, make sure you understand that c is our way of acknowledging the inherent ambiguity when we go from a derivative back to its original function. The family of antiderivatives. The first bullet point states, because c can be any real number, the result of an indefinite integral is not a single function but a collection of functions. So, remember that c represents any number. It could be positive, negative, a fraction, an integer, anything you can think of on the number line. Because c can take on infinitely many values, when we find an indefinite integral, we don't get just one answer. We get a whole group of possible answers. This leads us to the next point. This collection is known as a family of antiderivatives. Think of it like a family of related functions. They're all slightly different, but they share a common core. Now, let's look at the mathematical representation. If f of x is an antiderivative of f of x, then the general form of the antiderivative is f of x plus c, where c belongs to the set of real numbers. What this means is, if we find one function, let's call it f of x, whose derivative is f of x, then all possible antiderivatives are represented by that function plus any constant. See the curly braces and the notation. C belongs to the set of real numbers. Simply emphasize that c can be any real number. Let's solidify this with an example. The slide says, example, the family of antiderivatives for cosine x. We know that the derivative of sine x is cosine x. That's a fundamental derivative we've likely seen before. But, as we saw on slide 2, constants disappear when we differentiate. So, however, the derivative of sine x plus 2 is also cosine x, and the derivative of sine x minus 5 is also cosine x. If you take the derivative of sine x plus any constant, you still get cosine x. Therefore, the slide concludes. Therefore, the antiderivative of cosine x is not just sine x, but the entire family. Sine x plus c, it's crucial to remember that plus c is not just an optional addition. It's essential to represent all possible antiderivatives. Okay, let's move on to slide 4. As we've discussed in the previous slides, finding an antiderivative isn't always straightforward because of those pesky constants. Now, we're going to formalize that idea. This concept of a family of antiderivatives will be important as we move forward, especially when we start looking at initial value problems on the next slides, where we'll use specific conditions to pinpoint a single function from this family. Real-world analogy, velocity and position. So, it says, a practical way to visualize this concept is through physics. Imagine you are told that a car is traveling at a constant velocity of 60 kilometers per hour. Think about it, velocity simply tells us how fast something is moving and in what direction. Now, the slide points out that the velocity is the derivative of the position. Remember from our earlier discussions that differentiation gives us the rate of change. Position changes over time, and velocity describes that rate of change. Therefore, velocity is the derivative of position. Then it says, if you integrate the velocity, you can find the position function. This is the reverse process we've been learning about. Integration allows us to go from the rate of change, the velocity, back to the original function, the position. However, and this is the crucial part, knowing the velocity does not tell you where the car started. Let's say the car is traveling at a steady 60 kilometers per hour. That tells us how it's moving, but not where it is. It could have begun its journey at kilometer marker 0, or it could have started at kilometer marker 10, or even 50. There are infinite possibilities. In this scenario, the slide explains, the starting point is the constant of integration. C, that initial position, that unknown starting point, is what the C represents in our indefinite integral. It's the arbitrary constant that accounts for all those different possible starting positions. Finally, it states, to find the exact position, you would need an initial condition, a known starting point. If we knew the car started at kilometer marker 0, we could plug that into our position function, which would include C, and solve for C, giving us a specific, unique position function. Okay, let's move on to slide 5. This slide provides a really helpful real-world analogy to solidify our understanding of the constant of integration. This analogy beautifully illustrates why we need the constant of integration. It's not that we're bad at integration, it's that the derivative loses information about the original constant term. And just like needing a starting point for the car, we need an initial condition to pinpoint a specific antiderivative. This concept will become even more important as we move forward and start solving differential equations, so make sure you have a firm grasp of it. Theorem on functions with the same derivative. Okay, let's move on to slide 6. As we've discussed in the previous slides, finding an antiderivative isn't about finding one specific function, but rather a family of functions. This slide formalizes that idea with a theorem, a mathematically proven statement. It states that if you have two functions, let's call them f of x and g of x, and they have the same derivative over a certain interval. We denote that interval as I, then those two functions must differ only by a constant. Let me break that down. If the rate of change of f of x and g of x is identical at every point within the interval I, it means one function is essentially a shifted version of the other. Mathematically, this is expressed as, if the derivative of f of x, which we write as f prime of x, is equal to the derivative of g of x, or g prime of x, for all values of x within the interval I, then f of x is equal to g of x plus a constant, which we represent with c. So, f of x equals g of x plus c. Think back to our earlier examples. We saw that functions like x squared plus 5 and x squared minus 10 both had the same derivative, 2x. The difference between those two original functions, a constant in those cases, 5 and negative 10. This theorem confirms that mathematically. Finally, the slide points out what this means visually. This theorem confirms that any two antiderivatives of the same function will look identical, but they'll be vertically shifted up or down on a graph. They represent the same family of curves, just starting at different y values. This is a crucial concept to grasp, as it sets the stage for understanding how we use initial conditions, which we'll see on the next slide, to pinpoint a specific function within that family. Key takeaways. Okay, let's recap the key ideas we've covered regarding integration and antiderivatives. This slide, titled Key Takeaways, summarizes the most important points for you to remember. First, let's revisit what happens when we differentiate a constant. It states, derivative of a constant. The derivative of any constant, which we represent as c, is always 0. Remember, a constant is just a number, and the rate of change of a number is always 0. So, no matter what constant value we have, its derivative will always be 0. Now, building on that, we move to non-uniqueness. This is a crucial concept. Antiderivatives are not unique. Why? Because, as we saw with the examples on earlier slides, different functions can actually have the same derivative. Think back to the functions x squared plus 5 and x squared minus 10. Both of those functions, when differentiated, gave us just 2x. This means, when we're going backwards from a derivative to find the original function, there isn't just one answer. There's a whole family of possible answers. That leads us directly to the constant of integration. To account for this non-uniqueness, we add a symbol, c, to our antiderivative. This c represents any possible constant that might have been present in the original function before we differentiated it. It's a placeholder for an unknown constant value. So, when you find an indefinite integral, always remember to add plus c. Expanding on that, the next point is family of functions. The expression f of x plus c, where f of x represents any antiderivative, actually represents a whole family of curves. Imagine graphing several functions that are identical in shape to f of x, but each one is shifted vertically up or down. That vertical shift is determined by the value of c. So, f of x plus c represents all those vertically shifted versions of the same basic curve. Finally, we have the fundamental relation. This is a formal way of stating what we've been discussing. It says that if two functions, let's call them f of x and g of x, have the same derivative on a particular interval, then those two functions must differ only by a constant. In other words, f of x is equal to g of x plus a constant c. This reinforces the idea that antiderivatives are unique only up to a constant. Keep these takeaways in mind as we move forward. In the next slide, we'll discuss some common mistakes students make when dealing with integration, so you can avoid those pitfalls. Common mistakes. The first, and by far the most frequent error, is omitting the constant of integration. Remember from our earlier discussion that when we find an antiderivative, it's not just one function, but a whole family of functions differing only by a constant. If you forget to add plus c at the end of your indefinite integral, you're only finding one particular member of that family, a specific antiderivative, instead of the general solution. It's like knowing a car is traveling at 60 kilometers per hour, but forgetting that it could have started at any kilometer marker. You've got a position, but not the position. Next, a common misunderstanding is treating c as a variable. It's crucial to remember that c represents a constant, a fixed number. Think of it like the number 5 or -2 or pi. It doesn't change as x changes. It's not something you can solve for. It simply represents an unknown but fixed vertical shift. Don't treat it like x, which does change its value. Finally, let's address confusing c with coefficients. This is a subtle one. A coefficient is a number that multiplies a variable. For example, if we were to integrate 2 times x with respect to x, written as the integral of 2x dx, the result is x squared plus c. Notice that c is added to the result. It's not 2 times c times x squared, that would be incorrect. The constant of integration is always added, never multiplied as a coefficient. So the correct answer is x squared plus c, not c times x squared. Okay, let's move on to the final slide, which highlights some common mistakes students make when dealing with integration and the constant of integration. It's good to be aware of these before you fall into these traps, all right? Alright, that wraps up this section on the constant of integration and families of antiderivatives. Make sure you understand these concepts, as they are fundamental to mastering integration. Do you have any questions about any of these common mistakes, or anything else we've covered?